Okay, looks good. Can you maybe move forward and just to see? Okay. Okay, nice. Okay.
It's working. Yeah.
Okay,
Just
cool.
1 second.
Yeah.
Good. Well, then let me just introduce our seminar today. So thank you both to Marco and to Rongrong. So Marco is our speaker today, and Rongrong has graciously agreed to chair. So thank you. I'll turn it over to Rongrong to introduce our speaker.
Well, thank you, Daniel, and of course, many thanks to Marco for giving this seminar. And I just want to say a few words about Marco before we start. And so, as many of you know, Marco has been a long-time scientist in this field. He got his PhD from Nikhef and Utrecht University. And then actually that was working on NF49 at SPS. Then he became a postdoc at Berkeley. And then in 2007, he went back to the Netherlands and started to work on LHC. And then that was also then he became the convener for the JET group. And that was actually the time I had the chance to work with Marco. He was my convener. I was working on my PhD on jets in LHC. And then he played many different leading roles in the LHC. Currently, he's also one of the leaders in the LHC focal upgrade. He was a physics coordinator for LHC from 2017 to 2019, and the upgrade coordinator from 2020 and 2022. Of course, as you all know, that he is the LHC spokesperson since 2023. So yeah, one more time, welcome, Marco, and the floor is yours.
Okay, thank you. Thanks everyone for joining. Yeah, so I will try to guide you through some of the recent results, but in a somewhat big picture way of the LHC heavy ion program, and also then at the end introduce the future plans. I'm sorry for the mix-up with the time, so if the speech is not very smooth, that is because I didn't have a chance to go through before the lecture, which I would normally have done. And I was asked to keep it give a broad overview. So I narrowed it down a bit by focusing on the LHC. I should also confess that as the LHC spokesperson, you will find that the talk is a bit slanted towards LHC results, just because this is what I had in my slide collections and in my mind. It will not only be that, but it will be a bit biased. That's my fault. Okay, so let's go ahead. So now just a quick reminder, you probably all know, but the Large Hadron Collider is the largest accelerator in the world and the highest energy accelerator in the world. And about a month a year, we collide heavy ions, lead mostly. And there are 4 major experiments. There's the CMS and ATLAS experiments, which are large multi-purpose mostly PP detectors, but they also have a heavy ion program. You will see some plots from those throughout the talk. Then there's the ALICE experiment, which is the dedicated heavy ion experiment with a capacity to track in high particle density down to low PT and to do particle identification. And the LHCb detector is a forward detector that is optimized for heavy flavor physics, but also does some heavy ion physics and also other hadronic physics. And the collision energy for lead collisions was 2.76 TeV in run 1, and then 5.02 TeV in run 2, and it is now 5.36 TeV. And I think you'll see mostly results from the 5.2 TeV era. And next year we will have also an oxygen-oxygen and a proton-oxygen run. And in the past we had xenon-xenon collisions. But for the sake of simplicity, I will skip many of these things. So now, just before we start, I just wanted to somehow give you my bigger picture view of the let's say heavy ion and QCD program at the LHC. I just wanted to remind you that besides quark-gluon plasma physics, which this talk will focus on, there's also a lot of work going on what I would call multi-body QCD, so the dense system physics in PP and PLED. I'll show a little bit about that. Multiple parton interactions, hadronization mechanisms, which are also relevant for our field. The initial state, of course, and also hadron physics, the structure of exotic hadrons, the properties of hypernuclei and interaction potentials. This is a part that I will not touch upon, but is actually quite a broad, quite a big part of what is happening at the moment at the LHC. So then with that, let's dive in. I've tried to build the talk up a little bit thematically, and we start from the early stages, from the thermal radiation, where at LHC, measurements are difficult because there are large backgrounds. So what I'm showing here is the spectrum of, does this work? Yeah, of direct photon or photon production. And yeah, here on the right, you see it already after the subtraction of the decay photons, which are one of the challenges in the measurement. Now then you still have two sources of photons. One are what we think of as hard scattering sources, at high PT, the Quark-Gluon-Compton process, which also is present in PP collisions. And then at low PT, thermal radiation is dominant. And you see here, compared to the data, you see the black lines are these hard processes, and then you see an excess at low transverse momentum, which is the thermal spectrum. And in the paper that I quote here, we actually subtracted these hard scattering contributions, and then you're left with the spectra that you see here on the left, which are almost exponential and therefore look like a thermal distribution, and you can then fit them and measure the slope or the temperature. And if you look here on the right, we compare the temperature from such fits between RHIC and the LHC, and you see that these measurements from Alice, which are the solid points on the right, they have slightly higher temperature at RHIC, but not a lot larger. And part of the thing that you should keep in mind is that when you measure the temperature with photons, the blue shift plays a role. And I'll come back towards the end of my talk to dilepton measurements where that doesn't play a role, but where at the moment we do not yet have the thermal component isolated. But to give you a kind of a preview of that, another recent paper in this area, this is a measurement now of dilepton production. What you see on the middle is the dilepton mass distribution. And here it is, we focus on the low mass region where the Dulles decays of the pions are actually the peak that you see at the very low mass. So this is a way to subtract, or to, I should say, suppress the main background, which of photon and electromagnetic radiation, which is the decays of pi zero. So here at higher mass, you are then dominated by the thermal component, which is this orange line, as well as some of the higher mass hadrons. And you can use that then to extract direct photons more directly. And you see here on the right, you see the result. You see that at the moment, this is of course challenging because statistics are not so large. The uncertainties are large, but also this is consistent with seeing thermal radiation. More data will be needed to actually extract the temperature from this measurement. Now, another way to measure or to get access to, let's say, the pre-hadronic stage is to look at charmonia. As you know, charmonia has been proposed as a Quarkonia have been proposed as a probe of the early stage temperature. So if you produce CC bar pairs that bind into a kind of a pre-hadron, the screening in the Quark-Gluon plasma would cause a melting, which means that instead of producing a J psi, you produce two open charm mesons, a D and a D bar or something like that. And here on the left, you see a nice comparison. This is a rather old plot, but you see a nice comparison of the RAA, so the suppression factor for J psi as a function of centrality or multiplicity, compared from RHIC and from the LHC. And maybe somewhat surprisingly, what we see here is that at central collisions, the suppression at the LHC is much smaller than at RHIC. Now, and on the right, you see then PT differential measurement. So you see the same measurement, but as a function of PT for central collisions, again comparing RHIC and the LHC. And what you see is that while at high PT, the suppression at the LHC seems to be similar to what we saw at RHIC, what you saw at RHIC. At low PT, there's this large enhancement. And this enhancement, we think, comes from CC bar recombination. So from charm-anticharm pairs that may be even produced in separate hard scatterings that find each other and come out of the collision as a J-psi. And what this measurement then tells you is that that process is much more prevalent at LHC than at RHIC because there are more charm quarks being produced in each collision. So we don't only have the melting, but we also have the recombination. And even at high PT, there may be a more, instead of melting, you could also consider that there may be a direct energy loss process. Now you see here already that early model calculations describe this reasonably well. And this, I think, is one of the big new features at the LHC, is this very strong recombination contribution to the J-psi. And then if we look at the most recent data, so this is shown here, these are is now comparison of the RAA for the J-psi for forward rapidity, the blue points, which are an update of the measurement you just saw on the previous page. And the red points are now at mid-rapidity using the E+E- decay in ALICE. And there you see that at mid-rapidity, the let's say lack of suppression is even stronger, or the enhancement with respect to this kind of high PT baseline. And that is there a question or a remark? Okay, this I think we can take later, sorry. Or well, we can see, but so what I wanted to say here is that this larger enhancement at mid-rapidity is in line with what you would expect from recombination, where the larger density at mid-rapidity means that there's more recombination production. And you see here again that model calculations actually are in line with also quantitatively with what we measure. So the question in this chat is whether the difference can be the different rapidity intervals. Well, you see here that this is not likely. So the behavior at forward and mid rapidity is only different in this recombination regime. Now then, of course, at LHC, we can go one step further. We can go to the Quarkonia, to the bottomonia, the Upsilon measurement, where the same type of melting and recombination plays a role, but recombination should really be a much smaller contribution. And I thought it was nice to show here in the left and the middle, you just see the mass spectra of dimuons in this case, measured at mid-rapidity by CMS. And on the left, you have the PP spectra, where you nicely see the 3 different peaks from the psi 1, 2, and 3s. And then on the right, you see the psi 1s, the psi 2s, but the psi 3s is really very much suppressed. And then on the right, you see the RAAs that are obtained by analyzing this quantitatively, and you see very similar pattern to what we saw for the J-psi, but now with a large suppression in central collisions. So not so much recombination, and you see that for the 2s and the 3s, the suppression is actually very strong, and that much stronger than we see for the J-psi, and that has to do with melting temperatures and the probability for recombination and the feed down. These are all details that I'm not going into, that I also am not fully up to speed on. But roughly speaking, the psi 1s, the remaining psi 1s, they come from feed down, is my understanding. Okay, so this shows us the information that we have of the pre-hadronic temperature, and now I would like to switch gears and go to the, let's say, the QGP phase, where we study elliptic flow as one of the main signatures of what happens in the QGP and one of the main ways to analyze the properties of the QGP in this fluid phase. Now, I think, again, this is something you are quite familiar with. So here on the left, you see a picture of the initial state if you assume that this is a Glauber calculation, where you assume that the protons and neutrons that interact, that are within one radius of each other, they form the interaction zone, and the rest disappears down the beam pipe. And I've added this picture because I think it very nicely shows how irregular the initial state shape is. So the early calculations always assume that you have a smooth element, but you see that this is not the case. and that you in fact have higher harmonics like the third and the fourth order harmonic, and they are actually indicated here with these solid lines in the figure. And then starting from this initial state, the system expands, and that gives us momentum space anisotropy. So the cool trick here is really that the spatial anisotropy gets transformed into a momentum space anisotropy, and here you see the measurements that we do. So in the middle panel, you see the V2, so the elliptic deformation for different particle types. And on the right, you see V3 and V4, and there are in fact measurements up to V8, I think, for the integrated V2 or VNs. One thing I wanted to point out here as well is that you have this very characteristic mass dependence of the flow at low PT, which is consistent with having a common flow velocity. Larger masses pick up more momentum. And then at high PT, there's a pattern that is more like a baryon-meson splitting, which is consistent with the coalescence picture, that the fact that particles are formed via coalescence at this intermediate to higher PTs. Although at LHC, as some of the experts probably know, if you analyze it in detail, this coalescence scaling is not followed as closely at LHC as it is at RHIC. Now then, if we now want to go to a kind of a status to what have we learned, I think the way that this has now been done already for several years is with these Bayesian fits. And I think this is really a very powerful tool to both extract from the data what we can learn from the data, but also at the same time to explore the uncertainties that may still be there, or the model aspects that may not be controlled by the data. And just to illustrate that process, you see here the measurements, which here are the yields in PT and the integrated V2, V3, and V4 as a function of centrality. And then the method in this Bayesian inference is that you run the model with many different settings, and that is what you see in the top panels. And then you compare to the data, and you keep only the model curves that agree well with the data, and that is what you see in the bottom panel. And then from that, you extract the relevant medium parameters, as well as some parameters that are maybe not so interesting, and that tell you a little bit how robust you are against those, let's call them nuisance parameters. I'm not going to show you the full 14 parameters of this fit, but I would like to show here the main ones that we are interested in, which are the viscosity. So you see the upper panels are the viscosity as a function of temperature extracted from this fit. And then the bottom panel is the bulk viscosity as a function of temperature extracted from the same fit. Now, there are several groups that have done this exercise by now, so there are different results with slightly different error bands. But by and large, they agree on the top panel, where you see that the eta over S, the normalized viscosity, is close to 0.1, which is actually this limit, this quantum mechanical limit. And here on the right, you see the comparison to other fluids like helium and water, and you see that this rising behavior above the phase transition is what you expect for actually for a gas. But the value in the Quark-Gluon plasma is much lower than in conventional liquids. Now, for the bulk viscosity, you see that the uncertainty is very large. And this is, I think, in a way, the next frontier when it comes to extracting or to determining Quark-Gluon plasma properties. The bulk viscosity is something that we still have some work to do. Now, one other direction that people are going with these type of measurements is measuring the measurement of correlations. And there's actually a whole field out there, and I'm not going to belabor that in detail, but as one example, I'm showing you this figure, which is the correlation between the symmetry axis orientation of the second order and the third order, so the elliptic and triangular deformation. And naively, geometrically, you would expect that there is not much of a correlation, because the psi2 is defined fully by the azimuthal, by this ellipticity of the initial state, by the orientation of the two nuclei in the reaction plane, while the psi3 can be almost anything with respect to that. And you see here in the middle panel 2 measurements, and the new measurement is this Alice measurement, which you see here in red, which indeed shows very little correlation, and it's compared to an older Atlas measurement, which did seem to show some correlation. The difference here has to do with how you take out the effect of multiplicity fluctuations. And so the newer method actually shows that there is no strong correlation between psi2 and psi3, and that agrees with the theory models that you see here on the right, and also with the intuition that I tried to sketch earlier. Okay, so with that, I would like to wrap up this kind of chapter, and I just would, to keep the talk a little bit interesting, I would like to give you some discussion. So I think what we've seen is that and what we know is that both the analysis, the data analysis of flow harmonics, and these Bayesian fits with viscous hydrodynamical models are really a precision tool for QGP physics. And we already have a very high precision on the shear viscosity. And as I mentioned, one thing that I think is next is the determination of the bulk viscosity. I also wonder whether to make this really, to use the full precision of the tool, whether it would be good, or I think it would be good to more explicitly explore the 3D hydro. I mean, as you maybe know, in many of these hydro models, we use a 2+1D, so we assume boost invariance. And when you want to go to very high precision, such assumptions may play a role. So I think it would be interesting to explore that more. And then, of course, in particular at LHC, one of the steps that we're still working on is to determine the temperature evolution with electromagnetic radiation, which I think is, well, if you're critical, you say this is a cross-check, but I would like to emphasize that the information that we use so far is mostly from the freeze-out and beyond, and we kind of back extrapolate. So I think it is important to know how the temperature behaves in the early phase. And this may in the end be an input for understanding the equation of state, for which we have some handles, but not so many yet. So I think this is really worth pushing as well. And then, of course, there is the direction of exploring the limits of thermalization. Where does hydro break down? What do you need to have a hydrodynamic system? And there the small systems measurements and heavy flavor flow play a role. And I'll briefly go over a few recent results in that area. So as you may know, we have seen in PP collisions that there is also a long-range correlation, which looks very much like V2, like flow. I try to get my pointer back. It worked earlier. No, it's not. It worked earlier, but not anymore. So back to the small system flow. So what you see on the left is the LED result. These are two particle correlations with a trigger and an associated particle at fairly low PT. And you see this elongated structures, which are V2. If they're long in delta eta, this means that they are from the early phase of the collision. And then in PP low multiplicity, you only see a near side peak, which is a jet-like peak. And then on the away side, you see a ridge, which is actually the away side jet, which is not correlated in eta. And then if you go to high multiplicity PP, you see again this near side large delta eta peak. And also the away side peak is more flat than more independent of delta eta than what we saw in the low multiplicity. And so that shows that there is a flow-like effect in PP collisions at high multiplicity. And now this we now have seen, this is one of actually the first LHC results that was presented in public. But we have been, of course, analyzing that in more detail. And I think one very nice set of measurements is shown here, where we look at the particle type dependence of this effect. And you see on the left, charged particles, kaons and lambdas, and on the right, charged particles, pions, and pions, and protons. And you see again this kind of mass ordering that we also saw in lead-lead. So this raises the question whether this is pressure-driven, whether this is a collective flow velocity. And then to show a more recent result, I wanted to show you this one where there's several versions of this, but where we really now push to a low multiplicity. And you see on the right is the RHIC yield. So it is near side large delta eta yield as a function of multiplicity. And you see that even down to fairly low multiplicity, almost minimum bias collisions, there is actually a sign of a small near side RHIC. And you can compare this to recent reanalyses of the lab data. This one is an Aleph paper, or is based on Aleph data, where this RHIC effect is smaller, even if you look as a function of multiplicity. So this shows that this is really typical for PP collisions and probably related to multiple interactions or final state scattering between the produced particles. Now then, one other way to look at small systems is by using so-called UPC collisions, so the ultraperipheral collisions where you actually have a photon radiating off the lead beam that then probes the other beam. And in this case, we also use a lead beam, but you can, you see here the PT dependence of these are J psi's that are produced in these UPC collisions. And there's a clear peak at small momenta. Small momenta means long wavelength. So these are what we call coherent interactions where the photon interacts with the whole nucleus. But the tail are incoherent interactions where the photon actually probes the structure of the nucleus and even of the nucleons. And here on the right, you see the T dependence, which is closely related to PT dependence, but is a more theoretically well-defined measurement of the J psi incoherent production. And you see that the spectrum is rather flat. And there's two sets of curves that are being compared with here. And the flatter curves, the green one and the purple one, are curves that are calculated where there is fine structure within the nucleus, where there are so-called gluon hotspots. And you see that this flat behavior that we measure is actually pointing in the direction of having hotspots with a small size, so large wavelength, small size, large momentum, small size. So I thought this is very interesting because one of the things we need to be able to really understand this small system flow, the effect or how the flow emerges in these small systems, is the initial state, is the kind of the lumpiness of the initial density distribution. So again, to bring a little bit of discussion to the table, I mean, one thing that people tend to ask is, do we see a quark-gluon plasma in high multiplicity PP and P-lead collisions? And while I think this is a very stimulating question, I am not sure I really know what the question means. And there's three stumbling points that I would bring up. One is, can you even think of a QGP with a radius smaller than the radius of the proton? Does deconfinement make sense at those length scales? Or maybe it means that at high multiplicity PP, we have a system that is much larger than the radius of the proton. But answering that question would be very interesting, I think. And the other question that you have probably seen discussed in the field is whether large flow really implies thermalization, or whether one can build up flow with incomplete thermalization, and how would that affect the flow? And I think the question has been raised. I haven't seen a real analysis of that in recently. And then, as I mentioned already, the initial density distribution is also an important open point, I would say, where we're also making progress, but I think it's good to have these questions clear on the in front of you. Okay, so now we again switch gears and we go to the hard scattering probes of the plasma. And as you know, the picture here is that things that happen with a sufficiently high momentum transfer, they happen early in the collision, they happen in initial state hard scatterings, and then the products propagate through the plasma and interact with it. And the main examples are high PT particles and jets, as well as heavy flavors, where heavy flavor, the momentum scale is set by the mass. And I'll show you again a few examples and a few main features of these results at the LHC. So what we normally start with are the PT spectra of the charged particles. And here you see, just to illustrate, you see the PT spectra measured at the LHC in PP and lead-lead collisions, and then normalized by the number of collisions or by TAA to get a comparison that is per nucleon-nucleon collision. And then, as you know, we normally look really at the nuclear modification factor, which is shown on the right, and this is the picture from the LHC. Now, what is important, I think, to keep in mind is that this suppression at high PT, we think it comes not from a kind of absorption, but really from a shift of the spectrum to the left. So the relation between that energy loss, the amount of energy loss, and the suppression actually involves the slope of the spectrum. And I'll come back to that in the next few slides. And then here at low PT, you see, of course, the effect of radial flow and things like this. Now, to come back to this slope discussion, I'm comparing here the RAA for charged particles between RHIC and LHC. So you see here in the black points, the Phoenix by zero measurement, which goes out to almost 20 GeV, although with large error bars at high PT, compared to RHIC, ALICE, and CMS. Of course, Atlas has also measured this, but I was lazy and plotted only those two. And you see here that at LHC, there is this very characteristic increase of the RAA with PT. At high PT, note that here at 100 or so GeV, we start to reach, well, it's actually beyond 100 GeV, we start to reach 1. And when we looked at the RHIC data without seeing this complete picture, we often assumed that at RHIC there is no PT dependence. But if you see it in this context, maybe at RHIC, this also starts showing up at high PT. Now, the other striking effect here is, of course, that the suppression at LHC is not much larger than at RHIC. And that is where this spectral distribution comes in, and where the fact that the RHIC spectrum has a spectral index of 8 and the LHC spectrum of 6 matters. So this, even though the RAA is not very different, the energy loss is actually quite different between those two energies. Now then, before I go on to the jets, I have one side note which I wanted to mention, because this is something that at RHIC we have been, at least I have been puzzled by, and I think we did some work at the LHC to try and understand this. So this is now about the centrality dependence of RAA. What you see here on the left is the RAA versus PT for different centralities, and all the gray ones are high centrality, so central, while then the colored ones are peripheral ones. And what is interesting to see here is that somewhere at 70 to 80%, we reach the highest value for RAA at high PT of about 0.8. And then as you go even more peripheral, you actually suppress, you reach more suppression. And you see that also on the right. This is at the average from 8 to 20 GeV. So central means a lot of suppression, then it goes up, but instead of keeping going up towards peripheral, it goes down again. And by analyzing in narrow centrality bins towards peripheral, you can actually see that trend. And what's interesting to realize is that you can compare this to what we see in PP. So these are ratios of PP spectra at different multiplicity compared to minimum bias. And there you see that if you go to very low multiplicity, you actually also see a suppression. And so part of what we think is happening here is that in very peripheral events where you bias the collisions to have very low multiplicity, you bias even the PP collisions, and you get this suppression from basically from the PP collision dynamics. So that is why RAA doesn't go to 1 at peripheral collisions, which I think is a very interesting insight. Now, with that, I would like to switch to the heavy flavor. So as you know, we can also do these measurements for example, for D mesons. And note that this here on the left is the RAA. This is a log scale. So the high PT range is what you see here. And then at low PT, you see an increase. Now, in this case, the increase does not come from, for example, protons, but it comes from to my mind, from the fact that you have charm conservation, that the charm quarks, once they're produced, they come out as a charm hadron. So you can only rearrange them in PT, but you cannot make them disappear. That's very difficult. So to get the energy loss, you look at high PT, but to get interaction strength and overall normalization, you look at low PT. And then on the right, you see also the V2 for elliptic flow. And that's interesting to realize that the initial production is really azimuthally uniform. And so all the effect of this V2 has to come from interactions with the plasma. So this really shows that heavy flavor is moved around by the plasma. Then one can discuss a bit in detail how that works. And for that, I just wanted to remind you that we have kind of two pictures for the mechanism behind V2. For let's say light flavor and low PT phenomena, the hydrodynamical expansion that I tried to sketch on the left is the main mechanism as far as we know. So you have a fluid that expands and then hadronizes, and the common velocity imposes the V2. While for things like heavy flavor, it is really interaction driven. So you have initial anisotropic production and then interactions which can either be radiative energy loss, but can also be rescattering, more diffusive energy loss. And that generates V2. And so heavy flavor at high PT, at low PT, kind of interpolates between these two regimes, where if they fully thermalize, they would move with the liquid, but if they don't, they would be more in the right-hand picture. So what people have done also there is to do this Bayesian fits now to extract not the shape of the medium, but rather the transport properties, to extract the diffusion coefficient and the Q hat, which governs the energy loss. And here you see then the result. So you see on the left, you see the diffusion coefficient as a function of temperature. And on the right, you see the Q hat, which is the high PT transport coefficient as a function of temperature. And what I think is really impressive here is that already now our data constrain not only the value of these coefficients, but also to some extent the temperature dependence. So we don't only know at the phase transition temperature, but also above. Now, one thing that I think we still need to work on in the field is to understand the mapping or the relation between these two coefficients, because as you may know, there is a kind of a separate calculation going on for low PT where you use this diffusion coefficient and you use a Boltzmann-Langevin type description. And at high PT, there's the radiative processes which contribute and may be dominant. And people have tried to combine the two or are combining the two, but a systematic analysis for how that works would still be, I think, very interesting. Now, taking this now one step further is by including beauty, where we do not yet have these kind of fits, but we have the results from the LHC. So here you see prompt and non-prompt D mesons on the left from Alice and on the right from CMS. On the right from CMS, there is also a direct measurement of beauty mesons and the non-prompt J psi's. And the trend that you see here is that at low PT, the REA for beauty is larger than for charm, meaning that the energy loss for beauty is smaller than for charm, although there is this, you have to go always via the spectral shape, of course, to get a quantitative estimate. But model calculations also reproduce this, and I think that's very nice to see that there's a clear qualitative effect here, that the higher mass particles lose less energy. That effect is qualitatively expected both for collisional and radiative mechanisms, so it doesn't really tell us which of these mechanisms is dominant in this case. Now, if we go to stay with the beauty sector, but now look at the azimuthal anisotropy at the V2, the picture gets almost more interesting. So here on the right, you see again prompt and non-prompt D mesons, and you see that the beauty V2 is much smaller than the charm V2, and was not shown in these slides, but I remind you that the charm V2 is actually quite similar to the light flavor V2. So this is a very interesting trend, this shows that now we are reaching, we have particles that are not fully thermalized in the medium, although the error bars are still large. So with the coming upgrades, we will do better in this measurement. And if you look on the left, these are now the charmonia and bottomonia, the J psis and the upsilons, where again with kind of large uncertainties, but the upsilons show no sign of V2. So this almost suggests that the beauty quarks do not flow at all. And what I think is here an interesting question that we need more quantitative data for, but also more theory work to try and understand whether that maybe means that the B meson, the open B meson flow, comes mostly from light flavor quarks. You have a heavy and a light quark, and it could be that in the hadronization, the heavy quark gets dragged along with the light quark, although that seems unlikely, but this is the type of things we should be discussing in the field, I think. And in fact, this has also been done for the small systems where you see similar trends. So here, these are Atlas and CMS measurements. On the left are the semi-leptonic decay muons. The blue from CHARM, they agree with the charged particles. This is now in PP collisions. While again, the beauty shows no significant V2. And on the right, it's similar that here you see actually that if you do this for hadrons, that even at low PT, there is quite a difference in the way the PT dependence goes for light hadrons and D mesons, which you might expect based on the mass. But then the beauty mesons, they do not seem to show any flow in the small systems in PLED in this case. So that seems to show that we can actually get away from the fully thermalized system, which to my mind is an important part of proving that we actually see thermalization. The fact that we can switch it off makes the case stronger. Now then, as a final set of experimental results, I would like to show a few examples of jet measurements. So jet measurements are kind of the pinnacle of high PT measurements at the LHC, and you see here some event displays just to show you what that looks like. You see on the right a nice event display with 2 jets from CMS, and you see that even though we have a lot of energy in the underlying event, these are the small boxes that you see, the leading jets stick out very much, and this is a 200 GeV jet, and already here you see that the sub-leading jet, the recoil jet, is much lower energy. And this you can analyze quantitatively with this dijet imbalance measurements, and you see an example on the right where the blue distribution is from proton-proton collisions. I would like to remind that what you expect naively is that the 2 jets have a perfect momentum balance. But then you have next to leading order effects, you have finite jet cones and so on, which means that this gets smeared out. And the result of that is the blue distribution. It peaks at 1, which means equal energy between the 2 jets, but it has a broad distribution. But then if we compare to lead-lead, the red points, we see that in lead-lead there is actually a much larger asymmetry in these central collisions. So this, I think, is a very nice illustration that even these high energy jets lose a lot of energy in the Gluon plasma. And then what you can do is you can compare the RAA for jets, which are the green points on the right, with those for charged particles that I showed before, the blue and red points. And on the left, I'm also showing the spectra to show that if you actually compare the jet spectra and the charged particle spectra, the shape is not that different. So there's many more jets at a given PT because you count more energy. But the shape, the spectral slope is not that different. So the difference that we see on the right between these RAA values comes partially from a difference in energy scale on the horizontal axis. But it also has an interesting qualitative difference. So the blue, as I mentioned before, has this characteristic increase, which is actually compatible with a constant energy loss. So if you put a fixed delta E of 7 GeV in a really Mickey Mouse calculation, you get the blue curve, which goes through, which goes well through the data points at high PT. But the jets seem to show a trend that is much more constant as a function of PT, and that actually would be consistent with a constant fractional energy loss, a delta E over E that is in this case, about 15%. And it extends up to PTs of several hundred GeV. So that is really impressive. That means that you can have also 100 GeV or so energy loss at these very high PT. So this, I think, is really something that these jet measurements bring to the game. And this difference in shape of the REA, I think, again, needs a little more study. It would be nice to reduce the error bars at high PT for the charged particles and to extend these jet measurements over a broader range. But if it persists, then it indicates an interesting difference between jets and charged particles, which might be related to the fact that in jets you have many particles that can radiate and lose energy. Now at LHC, we also try to study this more directly, and I will not go through the full richness of measurements that is done, but just to give you a flavor, one technique that is being used there is this declustering, is where you take a jet and you peel back the clustering algorithm, and that allows you to identify, let's say, hard splittings within the jet, and that's sketched here on the left. And then you can do different measurements. You can, for example, measure the number of these hard splittings. That is shown here. So that's a distribution which peaks at about 2 or 3, and you can compare between PP and lead-lead. And you find that with these settings of the analysis, you actually have slightly less splittings in lead-lead than in PP. So it is not so easy to pick out the medium-induced splittings, which would be, of course, the real direct observation of energy loss. Would be very nice if we could do that, but that turns out to be quite tricky. Now, and then on the right, you see a similar analysis for charm jets, where this is a comparison for charm and inclusive jets in PP, and you see that the charm jets have actually fewer, no, I mislabeled it, more splittings than the charged particle jets, and that so that gives us sensitivity to the splittings with a kind of an identified leading quark. Now, another type of measurements that you can do with the same technique is you can look at the distribution and momentum distribution. So here on the left, you see what is called the ZG. So this is the splitting, the fraction, the momentum fraction in the splitting, but the comparison between the momenta of the two subjets. Again, compared between PP and lead-lead. And in this measurement, there is actually not so much difference. At the higher PT, you do see some differences. Or looking at the opening angle, again, with the idea to try and see whether there are large angle splittings that come from medium-induced radiation. But also here we see that, in fact, the data show more of a narrowing than a broadening. And that may have to do with, that probably has to do with bias effects. When you select jets with 60 to 80 GeV, you already lose some information about the energy loss. And so one of the directions here that is being followed is to do these similar measurements for photon jet pairs, where you can tag the initial energy. Okay, so with that, I would then briefly want to walk you through some of the future plans. So this is not meant to be an exhaustive thing, but just to give you a sense of where we are. So the LS detector has been upgraded in the long shutdown that was from 2019 to 2021. So we actually, in what is called now LHC Run 3, we are running with a much improved detector. We have about 50, we can now run at 50 kilohertz in PP collision, lead-lead collision. So we can collect 50 times more minimum bias data compared to the previous runs. And that is achieved by having continuous readout with a gem readout in the TPC on the upper right. And we also have this full pixel inner tracking system with an improved spatial resolution, which helps, of course, for heavy flavor measurements. There are several other upgrades like this fast interaction trigger and the online event processing to keep up with the data flow. Now, you can put that a bit in a timeline for the LHC program. Here you see the timeline for the upcoming run. So as I mentioned, we are now in Run 3, where Alice has had a major upgrade. Run 3 will go until the end of next year, and then there will be a new long shutdown of about 3 years, in which Atlas and CMS will do major upgrades. And you see here some pictures. The main upgrades, I'd say, for heavy ions are new trackers where they can do heavy ion tracking up to eta equals 4. Timing layers, which will also provide particle identification. They are meant for pile-up rejection in PP, but they also give particle identification, which is, of course, of interest for our programs. And new CDCs for, I think, also both Atlas and CMS. Then there will be run 4, and in that run 4, we also, Alice will have a few minor upgrades, in particular to the ITS and the forward calorimeter. And then there will be another long shutdown for which we are proposing a complete overhaul of ALICE to build a detector that we call ALICE-3, which has really excellent pointing resolution, a large eta coverage as well, and uses then time of flight and rich detectors for hadron PID, a muon ID, and an EM-cal for electromagnetic probes and leptons. And I just wanted to give you a few outlook plots on the performance for these upgrades. So both the current and the future upgrades, a bit of focus on the future upgrades. So what you see here on the left is the dilepton spectrum, which is now an upgrade simulation. So it's a projection of the precision that we can reach with run 3 and 4. So with the current upgrades in ALICE. And you see here that you can actually measure the average temperature. You can measure the slope of the spectrum at the masses above 1 GeV. But this upgrade ALICE-3 that we are discussing, or that we have proposed now, is shown on the right. And there you see that the precision is even much larger. And you can not only measure very accurately the slope at high mass, but you can also look in detail at the rho A1 area where you can see signatures of mixing between those states. And then with that high statistics, you can actually do differential measurements like dielectron V2 or the measurements of the slope as a function of PT, which give access to the time evolution of the temperature, which I mentioned before, I think is a very important thing to nail down to really get the precision information about the plasma. And then with improved tracking in this ALICE-3, we can also, of course, do better heavy flavor measurements. And here I'm just showing some projections for the V2 measurements of lambda C and lambda B. For those measurements, also the Atlas and CMS upgrades will help. Of course, they will achieve performance that is similar to what is labeled here with the ITS-3. So that is our upcoming upgrade for run 4. And then you see that if you go to the very high precision of ALICE-3, you actually become very precise. And that will, I think, be the way to constrain transport coefficients and hadronization models. And then the pinnacle of constraining hadronization is sketched here. So if you look at the yields of hadrons as a function of their mass, and you include the charm families, you see this very interesting pattern. This is, of course, this is observed, but it's also what the statistical hadronization model predicts is a clear exponential dependence between the yield and the mass. And then what we also see is that charm is enhanced with respect to the thermal expectation. So you see the 3 lines of single, double, and triple charm that are enhanced with respect to the light hadrons at fixed mass. And you see that we already measured some of those, and we confirmed that this is the case. And now the goal for the upcoming runs and the upgrades will be to measure double and triple charm states, which are really an ambiguous measure of this type of thermal production of multi-charm hadrons. And you can, of course, also think of other combinations like the B sub C and the D sub S and all this program. To illustrate how well we could do with multi-charm baryons, I wanted to show you this new technique that we're exploring, which is called strangeness tracking. And the idea here is to use strange size, which leave hits in the inner tracking layers of ALICE-3, which are very close to the first layer is a few millimeters from the interaction point. So here in this example event display, you have 4 hits, and then you can use that to distinguish size that point back to the primary vertex and that do not point back to the primary vertex. And the ones that do not point back are from multi-charm decays. And you see here at the bottom, you see the decay chain that gives rise to the secondary size. And then on the right, you see a projection of how well we could measure the yields of these multi-charm baryons if they follow the statistical hadronization model. So this is really a clear opportunity with this very high precision tracking. So with that, I would like to wrap up. I hope that I've shown you that the LHC is really an excellent laboratory for QGP physics with heavy ion collisions at the highest energies and the largest temperature and lifetime, of course, as you see on the right. I've tried to walk through some of the main observables and their implications: thermal radiation, the melting and recombination of Quarkonia, the transport coefficients, and the limits of thermalization, so the beauty and the small systems, as well as the interactions with the QGP and parton energy loss. And the upgrades for runs 3 and 4 and beyond will improve the precision and the reach. And I showed a few examples just to impress on you that for some measurements, I think this will really bring us the precision that we need, in particular for thermal radiation and for beauty, but also, for example, for gamma jet measurements. So there's still a bright future ahead for the program at the LHC, although we have already learned a lot from it. And thanks for your attention.
Thank you. Thank you very much, Marco, for this very comprehensive and enlightening talk. And now the floor is open for questions. So please raise your hand if you have a question. Okay, Bern.
Yeah, Marco, thank you very much for a very wonderful overview talk. I have a question on slide 25, where you talk about the very peripheral collisions and the RAA in them. And this is really intriguing because, I mean, there are two ways to make semantic sense out of this. The one is to drop the use of peripheral in that case. It's really not about they're more peripheral. That's what you say. It is really that the individual nucleon-nucleon collisions become less inelastic.
Yeah, that's how we understand the
less particle production. So in some sense, we're confusing the audience by talking about increasingly peripheral.
Yeah.
Right? The other one is what actually is the origin of the behavior in proton-proton? Is there actually, does this have to do with how peripheral proton-proton collisions are? In other words, I mean, the proton is also not a black disk. It has a density distribution. And one would think that if protons collide head-on, then you have probably at very high energy more inelasticity than if you go to more peripheral collisions. So do we have any understanding that we're getting, from the data, what really this affecting the proton-proton collision means?
Yeah, very good question. And I also find this an intriguing topic. So in terms of from the data in PP, I've not decided, but what I can illustrate here is that in Pythia, the way that this behavior, because you have kind of a characteristic behavior here in these ratios in PP, can be generated or can be explained is by having, as you said, is by having a microscopic picture of the proton, and what they do is that the number of multiple parton-parton interactions becomes smaller. It has a geometrical, an underlying geometrical bias. So if you have a non-central PP collision, you have fewer parton-parton interactions. And if you put that in a Glauber model, and that is what this HG Pythia does, you actually get qualitatively the right behavior. That's the black line. So this black line, you should not look at very central because it doesn't do energy loss. It just does that effect, that kind of geometrical effect in PP. So that is a possible interpretation. Whether there is a way to experimentally test that further, I am not sure. People have done a lot of work with trying to bias PP collisions towards fewer and more parton interactions, and it is somewhat possible, but it is always quite intricate.
Okay, thank you.
Yeah. Move on, Alexei.
Yes, hello, can you hear me?
Yes, we can hear you. Go ahead.
Yeah, so first of all, thank you for this very nice overview. And I have a question for for the slide 8, right? If I read the legend correctly, we are comparing a little bit different ranges in rapidity. And I mean, to produce those RAA, we use some kind of a dn over dy distribution, right? And for PP as a wrapper point, and then for the nucleus collision. But dn over dy is not a linear, and maybe that is the main reason to this discrepancy.
I'm not sure I completely follow you. You said the dn over dy is not linear as a function of rapidity, or
yes. And then yeah. So you see, for Alice, you take 2.5 to 4 in rapidity.
Yeah.
So it's a forward region.
Yeah.
But for the Phoenix, we have 1.2 to 2.2 from both sides, right? Yeah. So I would naively expect this to be different. Maybe not in the same manner as on the plot, but the more informative, I would say, comparison would be to take, for example, Alice mid-rapidity results, which I think you have, and to compare them with mid-rapidity from star or from few, maybe from star. So if we compare the mid-rapidity to mid-rapidity, wouldn't that be better?
So I agree that this is a question. I note that in these ratios, we do take the PP at the same rapidity interval. So the first order effect that the production depends on rapidity is taken out. Here on the right, now on this slide, you actually see for Alice the comparison between mid-rapidity and forward rapidity. And you see that at high PT, the suppression is very similar. And then this behavior at low PT is a bit different. My guess is that the star results at mid-rapidity would be at about 0.3 and constant. But I even suspect the plot exists, but I don't know what it looks like. So it's a good question, but I think we indeed have the information to answer it.
Yeah, if I can follow up on that, yeah, indeed.
Yeah.
So star, we measured the JSI-RAA in mid-rapidity. I think the rapidity less than 0.5, it's around like 0.4. But at the LHC, you see like it's higher, above 1, right?
Yeah.
Okay, cool. So any other questions? So maybe I can ask one. I'm not even sure if maybe Jürgen, go ahead.
Well, I just wanted to answer also to Bernd's point. Now, the first thing to remember is that this so-called peripheral bias starts already to be visible if one believes Pythia around 50%. So in the middle of the plateau. That's when it starts to deviate from 1. It's a small deviation to start with, but depending on the accuracy, you want to compare data and your model to, you have to start worrying about the fact around 50% centrality. And then it becomes big if you go to 60 or 70. And the reason, as Marco already said, is really, if you see PP as a small heavy ion collision, because at these high energies, One proton has about 30, 40, 50 constituent quarks, which would scatter multi-particle interactions. Then just the proton-proton collision itself becomes peripheral. And that means you have less multi-particle interactions. And then at the end, you get a second effect, namely that there's a dynamical bias on each of these. So they become not only fewer, but also have less multiplicity. So at the end, it's a selection bias, and it starts off with the impact parameter bias. And that's something really to start worrying if you are at the level of 5% accuracy, around 50% centrality. Okay.
Yeah. So, okay, so I think we can take with the comment. So, anyone else? So maybe I can ask a slightly provocative question. I'm not even sure that's a. So in the end, so of course I agree that you have there's a bright future. We have many years of running and also the upgrades coming. So what is the end game?
That's an easy question to ask, and not such an easy question to answer. So I think that one of the things the two things to my mind that we should come to grips with one is the equation of state. I mean, either see whether we can constrain it from heavy ion collisions. I know that some work has been done, and it looks like we can. And as I mentioned, I think that independently measuring the temperature is really also an important ingredient for that. But it's not an argument that I've worked out in detail. So I think that is a very important direction. And the other one is this. I mean, or one of the other ones is the end of thermalization. So how do we now really have proof? Do we really? The only way that all these observations can hang together is it if we approach thermalization in lead, and I mean, ideally, we would know how that is different from these high multiplicity PP effects that we see. That last part may be more of a theory question or a phenomenology question than an experimental question. But as I mentioned throughout the talk, to my mind, measurements of the beauty thermalization are really a part of answering that question, as well as the multi-charm chemical equilibrium probing. I mean, those are two aspects of thermalization. One is the chemical one, and one is more the kinetic one.
Sure. Okay. Okay, then we have two more questions. Ming Ray, I think. Go ahead.
Oh, hi, Michael. Thank you for your nice talk. I have a question on slide 21. Yeah, it is great to see that the question, do we see QGP in high multiplicity PP and periodic clearance is divided into 3 sub-questions. For the last 2, we can kind of get some information by looking at some flow observable or heavy flavor flow observable. But for the first sub-question, I want to know what observable should we look at to answer this kind of question?
Yeah, very good question. So to my mind, this first question is mostly a conceptual or theoretical question. What is the smallest QGP that you can make? And if you make something that is hot and smaller, why is it not a QGP? But those are the questions I have. And this is, of course, an experimentalist view of field theory, which is not the best way to look at field theory. But one thing that I could imagine that we could work on is, I mean, one handle that we do have is HPT measurements of the size of the system. So, and people have done this, have looked at the size of the effective size of the proton-proton collision at higher multiplicity. And if I remember correctly, there is a small increase in size. So maybe part of the answer is that in very high multiplicity PP collisions, the effective collision zone is actually larger than a, let's say, typical hadron. I write proton, but of course it doesn't exactly have to be a proton. And in fact, in a way, the second question is also somewhat of a theory phenomenology question, although there we can, by scanning system size or density, we can also help from the experimental side, of course, or by looking at different aspects of thermalization and so on.
Okay, thanks. Yeah, thank you, Marco. Daniel.
Yeah, so first of all, thank you, Marco. Very, very informative talk. I'm really interested in this future period that we're coming into, and Rongrong's question touched on this. What I wanted to ask is, as the US moves more and more into the electron-ion collider period, how do you see synergy or complementarity between the LHC physics program in the heavy ion and hot QCD side, and then the EIC on the cold QCD side?
Yeah, that's also kind of a big but more sociological question. So, I mean, one thing is, of course, that clearly, I mean, the community is, there's partially these two communities, the cold QCD and hot QCD, especially EIC, are one community or have a large overlap. So I think some people will work in both areas. And there will be synergies just from that fact. I mean, you've probably seen talks about jet measurements and using jets to analyze the matter in lead, and which I discussed, but also this is being thought about for electron-ion collisions. Then there is, of course, the effect that you with EIC you can measure some of the initial state aspects that inform the heavy ion community. Another important area where there is overlap is actually in detector development. So some of the detector developments that are being done for Alice have already made their way into the RHIC program and will probably also make their way into the EIC program. In particular, you may know the pixel sensors that have been developed for the ITS are now being used for S-Phoenix. And in fact, the EIC community is looking at building a tracker with the next generation of those sensors. And when it comes, for example, to particle identification with the RHIC, there's also active exchange between the people wanting to build a RHIC for LS3 and those who are working on a RHIC for the EIC. And similarly for the forward physics at the LHC, there's both detector synergies, but also the focal at the LHC and the other forward measurements will continue to probe the lowest possible X. And some of these measurements at forward rapidity or UPCs at the LHC will probe lower X than the EIC can probe. So I think clearly we will have to keep comparing nodes to understand where we are. So to me, there's many areas of synergy, but there are also clear differences. And I also expect that some people in the US, for example, who have a very strong interest to keep doing hot QCD, they might stay in the LHC program or even move to the LHC program if they would like to pursue that.
Yeah, thank you. Exactly. I think there's a lot of overlaps. Thank you.
Mm-hmm. Thank you. So last call for questions or comments. Okay, if not, so I think we can conclude today's seminar. So one more time, many thanks to Marco for this very comprehensive and very nice talk. And I don't know if there are any last minute word from the organizers before we close. Daniel?
Yeah, so thank you again, Marco. We really
You're
appreciate
welcome.
the time and the flexibility to be here with us today. Our next seminar will be in 2 weeks on on March 26th. That's a Tuesday. And I do apologize for all those in Europe. I will correct, based on the US time change, I will correct this in the emails so that it's correct and 2 p.m. CERN time going forward. We'll have our next seminar in 2 weeks. I'll send the announcement about that shortly. And we look forward to seeing all of you there and having more fruitful discussion. So thank you again, Marco, and everyone for joining today. And we'll see you in 2 weeks.
Thanks, everyone.
Thank you. Bye, Marco. Bye, everyone.